All right, here we go. Right, so I'm going to talk about a method for extending some dynamical downscaling of global climate projections into the Bering Sea. Oh, let's see now. Okay, and that should have advanced. All right, I'm just hiding some of the other windows here. Okay, good, that's better. Yeah, so we are downscaling global climate projections to the Bering Sea. On the left here, you will see our regional model domain spanning the Bering Sea shelf and the deeper Bering Sea. On the right are some details regarding the Bering Sea. There's an inner shelf 0 to 50 meters where tidal mixing is very strong, mixes everything top to bottom. Middle shelf where you have seasonal stratification, very strong stratification, and an outer shelf where stratification is weaker. Ice and tides are both very important. Here's our biogeochemical model. This is a nice diagram by Kelly Carney. It's published in 2020 and lays out the various parts of the ecosystem we're including, multiple size classes of phytoplankton and zooplankton, as well as nitrate, ammonium, iron, and detrital components as well. Now, under the ACLIME program, which includes quite a few participants, many colleagues at the Alaska Fisheries Science Center, we previously downscaled CMIP-5 climate projections and use them in fisheries management strategy evaluation. And we are now doing similar things with CMIP-6 climate projections, the latest round. And among other things, the regional model projects bottom temperature, which is, can you see my, my pointer? Okay, I will, I'm not sure. I can't see anyone, so I don't know
yes,
what
we
the
can
response
now.
is. You can, thank you. Okay, great. Yeah, bottom temperature is a very important thing to project because it is a large determinant of where the fish go in the Bering Sea. So we downscale multiple global models under multiple emission scenarios. We did that for CMIP-5, and now we're doing it for CMIP-6, and use that in management strategy evaluation. We recently published many of the details of our dynamical downscaling under CMIP-6, shown in these two papers here, and the author list shows some of the many collaborators within the ACLIME program. So we utilized, once again, 3 different global models, and under CMIP-6, 2 different emission scenarios, now called shared socioeconomic pathways. One a very low emission scenario and one a very high. So we have an ensemble of 6 different realizations dynamically downscaled. Now the challenge, now I had a slide for this. Oh yes, here we go. The challenge in all this is fisheries management needs regional projections of climate impacts, but dynamical downscaling, although a very useful method to obtain these, is very expensive to run, frequently more expensive than the global models themselves. So the challenge is to develop a way to summarize the behavior of the regional model in response to various patterns of global forcing. So our most recent method, using more traditional statistics described in the 2021 publications, we start by taking monthly anomaly time series from the dynamical downscaling, looking at both the forcing and the regional response, and we develop univariate empirical orthogonal functions for each variable and each month of the year. So that gives us some spatial patterns and some modulating time series. Now through an additional set of steps that I won't go into the details of here, we use that to project additional sets of forcing onto those multivariate modes that we derive using the univariate EOFs And we use that as a method to project how the regional model might have responded if we had been able to afford dozens of different realizations. There are a variety of variables generated by the regional model that we could enter into this analysis. This just shows ones that we used in the multivariate method, some having to do with the regional model, some with the boundary conditions, and some with the atmospheric forcing. This shows multivariate factor, the leading multivariate factor that we obtained using that method. And basically what you're seeing here with the thick lines, the thick red, green, and black lines is under SSP 585, a whole bunch of things rising and falling together over time. And this is the pattern of how things rose and fell together for all the different variables and all the different months. The bottom graph just shows a spectral analysis of the time series in the top panel. Now, some of these stick out as having an especially strong covariance of rising and falling together over time. They include the bottom temperature on the shelf, also the surface temperature at the southern boundary, or the boundary conditions, surface temperature at the western boundary, the air temperature, and the atmospheric forcing. All these things seem to have a strong relationship. We checked the success of that multivariate method for each of the downscaling models, each of the global models used to drive this system. We compare the dynamically downscaled result with the statistically derived result and found a very good match in both cases for both bottom temperature, and here's one of the biological variables, depth integrated euphausids, also very important to fish. So that gave us some confidence that the method was worthwhile, and we used it to extrapolate to dozens of different IPCC runs of global forcing without having to dynamically downscale. We just used the statistical rules we had developed and get our estimate of how things might warm under the SSP 585 scenario, given all these different model realizations, global model realizations, that is. And here's a similar thing for euphausids. Now, can we do better with machine learning? We've already used some machine learning in that we've used EOF and PC analysis, but we want to try some more modern methods to see if we can relate the univariate EOFs to one another. We tried 2 recurrent neural network methods and one more traditional method. We tried nonlinear autoregressive network, or NARCs, long short-term memory network, or LSTM, and simple multivariate linear regression, which we'll call LM here. So in each of those cases, we train the model with one set of dynamically downscaled output and test it on a different independent set. As with the previously described method, we start with dimensional reduction. For each of the EOF modes, we arrange the PCs for each month into one continuous time series of monthly perturbation amplitudes. We used air temperature, zonal wind, meridional wind, southeastern boundary SST, and southwestern boundary SST, all to see if we can predict bottom temperature using these machine learning methods. The simple linear model would look like this. We'd say that the spatial pattern of bottom temperature equals some coefficient times the spatial pattern of air temperature, etc., for these different forcing variables. So we're trying to relate time series governing the evolution of their spatial patterns. So both NARCs and LSTM attempt to relate present and past states of some forcing and response from the present time all the way back to the beginning of the time series. They achieve this using recursive algorithms, and they're tuned by various optimization schemes. You might note that a dynamical model itself is also a recursive algorithm where you're predicting the state at some time based on the state at time t minus 1 and forcings at time t and time t minus 1. Our initial testing found the NARCS method to be rather unstable, so we decided to focus on LSTM and the linear model. If you're curious, looking under the hood a bit, this is the Wikipedia entry for long short-term memory network architecture. Basically, you have some inputs shown by X, you have some outputs shown by H, and the LSTM is also keeping track of some internal state shown by C here, which is influenced by the inputs and is influenced by the past state of the system, including the past states of the inputs. You might note there's some similarity here to an ocean model itself, in that you've got some longer term filtering of what's coming in. So we selectively withhold some of the data and train each of the methods and then see if it can replicate what we withheld. And here are the R values for each of those selectively withholding tests. We've arranged them here in order of success, that is the greatest R values. And we find that the LSTM using just the top univariate mode actually did the best. Adding more EOF modes didn't necessarily gain us anything. We tried various permutations of the linear method, and simplest seemed to do about the best, actually. Just a single mode, just focused on present time. Though you do gain a little something if you add past time, but it's rather modest. So here's the time series themselves. On the top is the linear method. On the bottom is the LSTM method. And you see that the lines in the LSTM method more directly correspond to one another. We have gained some additional skill. This is under SSP126. Here's under SSP585, where there's more of a trend over time. In some ways, the 126 is a cleaner test because it's a wider time series that we're trying to reproduce. Since the linear model involves simple coefficients, it's easier to interpret than LSTM. This is always a challenge, interpreting the results of a complicated machine learning algorithm. But we can go back to this simple linear model, and it seems to be telling us by the coefficient values for each of those terms that the boundary condition of SST is one of the strongest drivers of the bottom temperature on the shelf, followed by the air temperature that we're applying as a forcing condition, followed by the zonal winds. And in some ways, these are similar to results we found from previous methods. But here, zonal winds turned up as an especially significant term, and that was a little bit of a surprise to me. It had not turned up as much in some of these non-machine learning methods. So our conclusions thus far: a simple linear model does surprisingly well at fitting the primary forcing PCs to their primary response PC, using no memory or influence of past conditions. And as stated, the ocean boundary condition and on the south eastern boundary had an especially strong influence, followed by air temperature, followed by zonal winds. Although the linear model did very well, the LSTM method did even better, up to 50% more of the variance explained, especially when there was no trend in the series, as there is under SSP126. Some of the variants of the linear model gave us a slightly better fit, and adding additional EOF modes did not necessarily improve things. So that's where we're at so far, and there's plenty left to explore. Thank you.